Okay, well, welcome to UNLV and Frank Schumann lecture. So my name is George Rhee. I work here in this building. So I'd like to start by thanking Dr. Danny, wherever there he is, for supporting this lecture series, making it possible for us to all be here and continue. Just have a couple of things to say. We have an email list, so if you're not on the list and you want to know what's happening, you can sign up here after the lectures, and it's a couple of emails a year. We do these in the spring and the fall. And then we've also started a YouTube channel, so if you want to relive the experience or whatever, share it with your friends, like and subscribe, whatever you want to do. And we're posting these on our YouTube channel. That's all I'm trying to say. And yeah, that's about it. And so it's a pleasure to welcome Dr. Travis Fischer from the Space Telescope Science Institute. I'll say a couple of words about him, but just he provides support for the cosmic origin spectrograph aboard the Hubble Space Telescope. He was a NASA postdoctoral program fellow at Goddard, focusing on James Webb Space Telescope science. He has extensive experience with observations across the infrared, optical, and radio wavebands, lead investigator on several James Webb Space Telescope and Hubble Space Telescope programs. If that doesn't impress you enough, he's brought stickers of the Hubble Space Telescope. Take home with you. Welcome, Travis.
Hey, thanks. Yeah, thanks, George. Hey, everybody, can you hear me? There's not a microphone, so I'm projecting, hopefully, that this is going to work for everybody. Fantastic. Awesome. So, yes, I'm Travis Fischer. I'm at the Space Telescope Science Institute in Baltimore, Maryland. What is that? We are responsible for making sure that the Hubble Space Telescope and the James Webb Space Telescope are working into satisfactory order for scientists. The instruments on top of both of all these observatories need to be calibrated, and so we're always taking care of them. So I support the Hubble Space Telescope as 50% of my time, and the other 50% is what I get to do research, and I get to understand how supermassive black holes work. So I'm just going to be here to talk to you guys then a little bit about the research that I do, and talk about black holes in general, and then how they relate to what I look at, which are these active galaxies, where black holes are affecting how galaxies survive. Come on, let's go. Okay, great. So before we talk about what black holes are and what active galaxies are, let's just talk about what are galaxies, right? So galaxies are just going to be an accumulation of stars and gas and dust that is forming and swirling around itself just due to gravity. So these things have coalesced into this spiral shape. Here are several different images that we've taken with the Hubble Space Telescope of all of the stars and galaxies and gas in these galaxies. And in between all of those stars and all of that gas is a lot of nothing. It's kind of surprising to think about how galaxies mostly are just empty space. But so each one of these galaxies holds billions of stars like ours. And our sun lives in a galaxy just like those. It's called the Milky Way. This is a picture of our Milky Way galaxy. So our galaxy looks a lot different than everybody else's galaxy when we're looking at it, and that's because we're in it. So then here's a cartoon then of what the Milky Way we think it looks like today. And then there's an image of what we can see of the Milky Way, what it looks like when we observe it with telescopes. So maybe you see these images all the time of this large plane, but it's actually not just in front of us toward the nucleus, it's a 360 view. So whenever you're looking at those flat images of the Milky Way, it's us taking a full 360 around and observing all of the material around us. So we know that in most galaxies, ours included, there is a supermassive black hole at the center of it. So this is a picture that we were able to take of our supermassive black hole, Sagittarius A star. And so we're actually able to see some of the smallest radii before we are able to lose information. It falls into the event horizon of the supermassive black hole. And this is really a new thing. We haven't actually been able to image the black hole until only a couple of years ago. So this is some really revolutionary imaging. So then if we have a supermassive black hole at the center of our galaxy, people often say, well, what is a black hole? And so let's just talk about what we know about black holes. So we know how some black holes form. This is a massive star, an A-type star. It's more massive than our sun. It's about 8 times more massive. And then once it gets to the end of its lifetime, it's going to explode. It's going to go supernova. And then the remnants of whatever was at the center is going to collapse on itself and form a stellar mass black hole. Now, that star was 8 times the mass of our sun. It's going to be much larger than our sun. But the remnant, that stellar mass black hole, is actually much smaller now. All of that mass is compacted into a very small point and is only about 30 miles in diameter. That's about the size of Rhode Island. So you can kind of understand how these things are so dense, is that you're packing all of that mass into a very small amount of space. So we know about these stellar mass black holes, and we have a good idea about how they originate. But we also know about more massive black holes, these supermassive black holes. So here's our sun. And then for scale, this is what Sagittarius A star would look like next to it. So it is enormously massive. There's about 4 million times the mass of the sun packed inside of this event horizon. But it's only about 18 diameters of the sun across it. So again, you have this really massive object crunched into a size that's only just a little bit bigger than our sun. And then for reference, here's the Earth right there. You see it? So you can imagine just the scale difference between these two black holes that we're really familiar with. You had the stellar mass black hole, which was just a fraction of the size of Earth. And then you have the supermassive black hole that is many times that of the sun. So what are black holes? Black holes are not wormholes. They are not time rifts. They are not portals into another dimension. People are always asking, like, what happens if you fall into a black hole? And I'm like, I don't know. You're not going to like it. It's not going to be a place that you're going to want to end up. So you should never think of it as some sort of dimensional rift necessarily. Black holes are objects. Black holes are just like everything else that we're used to in this universe, but it's just their physics makes them a little bit more complicated. But they're the same thing as a jug of milk or a horse or Saturn. They're just objects that are in space. And the only difference between a black hole and any of these other objects is just that they're stupid compact, relatively speaking. So then people then ask, well, are black holes dangerous? Do we have to worry about these things? And so trying to think about that, you say, well, we can go swimming with sharks, and that would be fun, but you don't want to probably do that for too long. You'd have a bad time. So what do? We remove ourselves from the sharks. We go look at the sharks from far away in a cage. We're safe. Great. Volcanoes. Volcanoes are really exciting. We don't observe volcanoes on volcanoes. No, we remove ourselves from the volcano. We observe them from further away. And then we're able to learn all sorts of cool stuff, and we're not in any danger. So you can see where I'm going with this. Black holes, we don't want to be in a black hole while we're trying to study it. We want to observe them from far away. And that's what we do. We are at a very safe distance from every black hole that we're aware of, and that there's no sort of danger that's going to befall us from any of these black holes that are out there in space. The closest black hole, by the way, is about 1,500 light years away from us. So it's got some time, and it's not even looking at us. It doesn't even know about us. So we're going to be okay right now. So the reason people are afraid of them, though, is they think that there are these vacuums that are going to pull them in. But I want to tell you right now, black holes don't suck, you guys. So let's do a little thought experiment where we take our solar system. Here's a cartoon of that. And we're just going to pluck out the sun, and we're going to replace it with a black hole of equal mass. And so what would happen to our solar system then? Not a whole lot, because the planets would all keep orbiting that new black hole sun. The same thing would be happening. We wouldn't even notice that anything would have happened necessarily. We'd keep orbiting around it and be fine. We would freeze. That would be bad. So we would die that way. But that's a different talk for a different colloquium. So don't worry about that. But the point is that it's just an object of mass. And if we replace one object with another object of equal mass, nothing's going to happen to us. So just because it's a black hole doesn't mean we're going to get sucked into it. So how does a black hole work? You're like, oh, I can't ever escape a black hole, so that's pretty scary. So to kind of come up with an explanation, here's like a really simple equation that says, well, the escape velocity, the velocity that you need to escape the gravitational pull of something is effectively the mass of that object divided by your distance from the center. So for Earth, mass of Earth is 1 Earth, and the radius is 1 Earth radius. And then the velocity that you would need to escape the pull of Earth is about 11.2 kilometers per second. I'm a dude that doesn't know what that means in my brain. So effectively, it's a rocket. You guys, a rocket is going up there. It's going to be a little bit slower than 11.2 kilometers per second because we don't want to escape the pull of Earth's gravity forever. We want to just go around and orbit Earth and come back. So you can imagine, though, that it's going to be a velocity that's just a little bit faster than a rocket. But let's say we now replace Earth as a planet with Earth as a black hole. So the same mass, and now the radius of Earth is no longer 1 Earth radius. It is about the size of a ping pong ball. So, right. And so we put that back into our equation, and the required velocity to escape that black hole is 1 trillion kilometers per second. That means nothing to my brain. I have no idea how to fathom that. So instead, we can just say that's 3,000 times the speed of light. So photons aren't even traveling fast enough. These objects that don't have any mass aren't going fast enough to escape the gravitational pull of an Earth black hole. But photons don't have mass. That's right. But they do still follow the laws of physics in the sense that any object with mass can create a dent in the space-time medium around it. So here's like a quick cartoon that just shows a photon that is traveling around a very massive object. The path of that photon is going to be bent depending on how massive that object is. So we see this all the time in a lot of the extragalactic astronomy that we do, and that if there's a source of light behind a very massive object, and the massive object in this case is a cluster of galaxies. Like, not just a supermassive black hole, it's a supermassive black hole in the middle of a much more massive galaxy next to a bunch of other massive galaxies. So you have these huge lenses then that are bending all of this light around them. And so we see these galaxies that we would not be able to with our eyes normally. The light is enhanced and the light is refracted, so we get a bright, sharp image of these galaxies that we would otherwise not be able to see. Just a quick tangent, like this is a really cool star that I heard about. It's called Earendel. So this lens, the light from this one star was bent so hard around some massive objects in front of it that we're actually able to resolve the light coming from this one individual star. Could you imagine that we're seeing a star almost at the beginning of the universe, at the Big Bang, all the way back from the very beginning, we're seeing this one star hanging out. And so it's really neat way that we wouldn't be able to understand what stars did at that point in the universe without gravitational lensing. Okay, so we're back with our black hole. So the black hole dent in the space-time continuum is a lot stronger than that from a galaxy, or I'm sorry, from like a star or something like that. So when you get close enough to a supermass or a black hole of any sort, that photon is going to reach what we call the event horizon. And the event horizon, that's where the photon is bent so hard that it turns in on itself and effectively spirals into the surface of the black hole. And so that's how photons, even though they don't have mass and aren't able to lift off the surface of it as if it was a rocket, they also too cannot escape the gravitational pull of a black hole. So here's where things kind of get fun for me, is that we have black holes and then we can see them eat other objects. Here's a star, like, I don't feel so good, and it's getting a little close, and bam, oh my gosh, it is dead. That is the dead star. And so all of this material that was once that star is now spread out across many, many larger distances, and we can see shreds of it that are kind of forming around that black hole. That black hole is paradoxically being very bright right now. So here's another cartoon. There's a black hole lurking here, and there's a star that's so happy, doesn't mind what's going on, and oh my God, it's getting all of its material stripped away from it. And so what we look at then is what we call an accretion disk. So this black hole is eating material, it's accreting material, and all that material is swarming around that black hole. So when you rub your hands together, you can feel like a little bit of friction, and you can feel that heat, that's infrared light that's going to come out of your hands. But when you have that supermassive black hole with all the material coming out, it's not just infrared, it's optical, it's ultraviolet, it's X-ray, it's a ton of very violent, powerful radiation. So when we see these accretion disks around the supermassive black holes at the centers of galaxies, this is an event that we are trying to understand, and we call these events active galactic nucleus. An event is an active galactic nucleus, and we call that AGN for short. So whenever I talk about understanding AGN, I'm trying to understand these events where supermassive black holes are eating tons of material and then giving off a ton of radiation that is messing up the host galaxies that they live in. So, well, yes, as I just said, AGN are extremely energetic. So when you're emitting all of this radiation, it has to go somewhere. So we have this accretion disk that's kind of blocking the light from getting out on that axis. But then on the other axis, you get all of this outflowing of radiation. And what does it do? So I tried, again, numbers, really big numbers don't mean anything to our brains. So I tried to come up with some sort of analogy to understand how energetic this process is. And so I said to myself, okay, we're going to try to measure how much energy is coming out of a local AGN. We're going to take atomic bombs. We're going to take all the sand on Earth, and we're going to convert them to atomic bombs. And is that enough that's coming out of a supermassive black hole? And the answer is no. So what you actually need to do is you get 160,000 Earths, and you take all of the sand off of each one of those Earths, and you convert each of those pieces of sand into an atomic bomb, and you detonate those all at the same time. That's how much energy is coming off of an AGN per second.
That's bad.
That's right. Thank you. I couldn't agree more. So what does all of that energy do? So here is a very dark image taken from the show Chernobyl that came out a couple years back on HBO. Spoiler alert, Chernobyl blows up, people are sad. There's a bunch of radiation that leaks out of this power plant, and the people from the town over are looking at the radiation as it's lighting up the gas above it, the atmosphere above it. But it's not just lighting up the atmosphere above it, it's ionizing the atmosphere above it. All of the particles coming from that opened reactor are running into the air molecules above it and stripping off electrons and energizing other molecules, and then when they recombine, they create all this light. And I'm pretty sure it's blue because it's nitrogen, and nitrogen gives off a lot of blue light in the optical. And since nitrogen is the #1 element in air, that's why it looks to be so blue. So, taking from that, you have this ionization. All the particles are running in and frying this gas, and we can see that light then showing that this gas is being fried. Similarly, we see a similar process in our aurorae that are happening above the poles. So you have all of these particles from the sun that are traveling along magnetic field lines, and they're running into elements in the upper atmosphere. They excite them, and then those elements de-excite, and they produce the beautiful colors that we're seeing. So you're having some sort of particles that are running into an element to create this sort of emission process that we're trying to understand. So AGN kind of go through that same process. Here's a galaxy with an AGN inside, and all of that radiation then runs into the material surrounding it and ionizes it. That first part was like a Hubble picture, and then this inset is actually taken with a different telescope that gives us a little bit of a rainbow, a spectrum at each individual pixel. So it lets us understand what the gas is doing, how it's moving, if we understand the Doppler shift. So let's talk about the Doppler, whoops, never mind. This is what it looks like. Oh man, the ionized gas, it's so cool. So what you're seeing is a bunch of star formation in the host disk, But in the blue light, B, you're seeing this kind of like flashlight of doom, right? So that AGN had the accretion disk, and then perpendicular to that accretion disk, you had all this radiation that's flowing out into the system, into the host system, and it's frying all the material that's there. And if it's close enough to where the black hole is, it's actually pushing it out into the rest of the host system. Okay, back to the Doppler shift. How do we know that this is all happening? We need to understand what the Doppler shift is. So on Earth, we can understand the Doppler shift all the time when we see an ambulance go by. Right now, it's just parked. It's putting the guy into the ambulance or something, and it's emitting that noise, and people in front of it and behind it hear the same noise. However, if we have the ambulance moving, then the people in front of the ambulance have the sound waves pushed together. And so that has a higher frequency, and it sounds has a higher pitch. Whereas the people behind you, behind the ambulance, have a lower frequency because the sound waves are spaced further apart. Right? At a race car, something like that. So the same thing happens then with light if we're traveling fast enough. You have our light bulb, it's just on, everybody sees the same color because they're all having the photons travel at the same wavelength to their eyeballs. But if we have a light bulb moving at a fast enough speed, the wavelengths of those photons can either get pushed together or spread out. Again, same thing as what's going on with those sound waves. So the people that are in front of the light bulb see a photon that is blue, and then people that are behind the light bulb see light that is red-er. An aside, this is why we talk about when we're looking at galaxies or trying to understand the universe, everything has a redshift. We try to understand how far away a galaxy is by understanding its redshift, because all of the light that it's emitting, since it's traveling away from us, is going to appear intrinsically redder than what it would be if it was standing right next to us. So that's why we have the terminology redshift in astronomy. Okay, back to our data. So now we're going to take each one of those pixels and understand what the gas is doing in those pixels. Is it moving toward us or away from us? And so we can see that most of the gas then orbits the center of the galaxy. So this gas that's formed from the light that's formed from stars, we can see is kind of doing a disky motion. You kind of can remember what the picture behind this looks like. It's a disk kind of at an inclined angle. So the foreground is at the bottom, the background was up there. And so the upper left-hand side of the gas is redshifted. We can see that it's a little redder than it should be. So that means it's rotating away from us. And then the stuff on the bottom right is blue shifted. And so we know that that gas has to be coming toward us. So we can interpret this gas all to be in a rotating disk. Pretty easy so far. Then we look at the blue gas. The blue gas is the gas that's being fried by that AGN at the center of the galaxy. And we see it's doing something completely different. We see that this AGN is driving out this ionized gas radially. That means like spokes on a tire, right? It's going out away from the center in two different directions. The stuff above the plane of the galaxy is driven toward us, is blue shifted, and we can kind of see some of the gas that's behind the disk red shifted and traveling away from us. We don't see as much of the red shifted stuff because it's kind of hidden by that host disk. But we see the blue stuff really clearly. So what we can kind of see that's going on here is that you have the gas that's being pushed out by the AGN. It kind of runs into the host galaxy and kind of splashes up. So maybe you think about like the Little Mermaid and Ariel's sitting on the rock, and you can think about how she looks, and maybe if you just picture, and she's like, crash, and there's like the water shooting up. Can you guys picture it? You guys can picture it. Okay, anyways, so yes, so the gas then is driven out of the galaxy, and that gas is driven really fast. And so we use these units of kilometers per second. The gas that we're looking at travels at least 300 kilometers per second. I don't know what that means. Again, it's too fathomable. So I've created a graphic. We're driving from Seattle to Miami in 17.7 seconds. That's how fast 300 kilometers per second is. So it's about as fast as that animation, assuming you don't hit any traffic. So you can understand then that this material is booking out, and it has a lot of energy, and it's being driven out of the system, out of the galaxy. So it's always kind of fun to look at these pictures of these beautiful structures that are going on. We see them from afar, sort of like looking above at a hurricane. You're like, nature's amazing and wow, it's so beautiful, I love nature. But if you're like living inside of these things, it's horrible. You're getting fried by killer radiation and the material's being driven outward and stuff slamming into you and removing anything that you loved, anything that you ever wanted, it's gone. And so it's horrible, but we look at these things from outside and we never get to really understand that just by looking at it. So understanding like the kinematics and how that gas is being driven outward, we can see that these black holes are really having an impact on the hosts that they live in. So are we in danger? We have a black hole at the center of our galaxy. So we think that the Milky Way had undergone an active galactic nucleus event some 2 million years ago because we see these beautiful bubbles that are above and below the host galaxy system. So here again is the host galaxy that we remember looking at toward the nucleus. And we can see in higher energy bands like gamma rays, X-rays, and some radio, that there are these structures above and below. So what we think is happening then is that the AGN, the black hole, when it was active, blew the material perpendicular to the host galaxy system. And since we know from our way early on, we're about at least halfway out in the host galaxy, and this thing is pointed away from us, we're probably okay in any sort of case of a new era of AGN activity. I am not liable for any sort of repercussions that I just said. Do not come back to me if we are about to get torched by ionizing radiation from a supermassive black hole. Thanks. So how do AGN affect their galaxies? We're still trying to figure that out. That's why I kind of have a job that I get to be a little Sherlock Holmes detector dude, trying to put my cap on and trying to understand what these things do. Why are they important? They're cool. Do they do anything for the order of the universe? So gas is needed to form stars. So this is a flyby through the Orion Nebula. It's this nebula that's at the hilt of the Orion constellation. You can see it with your eye. And it shows that stars form when you have big clumps of dense hydrogen gas that are able to smoosh and gently combine on themselves until they get real tight, and then they get hot, and all of a sudden they start fusing that hydrogen together to form helium, and then you have these stars that just become born in these clouds, and they blow away all that material, and then they are revealed from these nurseries, and you're like, wow, little baby stars, that's so beautiful. But you need that material there to form those stars. So we think that supermassive black holes, AGN, have two different ways to affect that. And then, so as an analogy here is like when you turn your sink on and you're looking at the sink hit the bottom of when you see the faucet hitting the bottom of your sink, I think that is a nice analogy for what we're seeing in this AGN feedback process that's going on the left. So the first process is negative feedback. So the AGN is powerful, the material that is being driven out is small, and you're able to evacuate it from the nearby region of that supermassive black hole. That means we're preventing stars from forming. It's a negative feedback situation. Alternatively, at greater distances, the AGN power drops off because the light and all the winds are spreading out into a much greater volume, so you're not able to drive material out any longer. And then now you're starting to become like a snowplow, and you're pushing that material together. And then what we're calling this is positive star formation, because you're pushing the gas together, and that's going to help those little baby stars get the boost they need to form these stars. And so we're promoting star formation in this sense. So we're trying to understand which one of these processes is dominant, which one is important, and how often it happens. So when I put on my Sherlock Holmes hat and I'm trying to understand what's going on in AGN, we need to put together all of the clues from different wavelengths to really get the full picture. So that picture that I was showing you of this AGN is actually 3 composite wavelengths of X-ray emission, really high fried gas, radio plasma, which is kind of formed from electrons traveling along magnetic fields, and then the optical, which is just the optical response of the light coming out from that central nucleus and then being reflected into our eyeballs. So James Webb doesn't do any of those wavebands. James Webb looks at stuff in the infrared, and it's providing us another cool dimension of understanding what's going on in all of these different, in AGN and a bunch of different other objects. So like, here is the Cat's Paw Nebula. I have it here for you today to bring home with you. Please take one. I have 100. Do not make me leave with less than 100 or any more than 0. Take one home, please. And so it's just showing these nurseries again, where we're seeing the stars that are lighting up the surrounding material, ionizing it. We're seeing in a very close in-your-face level of the similar processes that AGN do at the center of galaxies at much greater distances away. So this is giving us some really cool clues on a micro scale on how feedback works versus the AGN that are much further away from us. And James Webb also lets us, again, not just look at these nearby things, but also the universe at large. And so here is the Hubble Extreme Deep Field. This is where Hubble just looked at a patch of sky for a long, long time, and it was able to suss out all of these little galaxies. Each one of these pictures, these things is a galaxy, by the way. There's no stars in here. And so these are all home to billions and billions of other stars, billions and billions of other worlds that we're just looking at. And then so Webb is able to give us even more information about what's going on. We're actually able to see like heat signatures of all of the gas that's surrounding these galaxies. We're getting a much deeper image thanks to Webb. And then in the middle, yeah, we come back to galaxies. So this is a galaxy that I was actually working on. I wrote a paper on this thing last year, NGC 4258. And so we got James Webb data, and they wanted to ESA, the European Space Agency, was like, we need a picture of the month. Let us take your data. And I was like, OK, it'd be great if you took the whole thing and made it into a picture for me so I could put it on a Christmas card. And they're like, sure, let's take a look. So it's really neat that I had a galaxy to look at, but every one of those like little specks down there is also a galaxy in the background. Somebody at work said early on that every image with James Webb is a deep field image. Like you're looking at something in the foreground, sure, that you're interested in, but there are so many galaxies in the background now that we're able to pick up with the sensitivity of James Webb's mirror, and also its sensitivity to the infrared. So we're seeing lots of little galaxies. All these little specks are all little galaxies that nobody's ever looked at before because we're too busy looking at the stuff in the foreground. So let's see. So then they made this image, but it's only the best rectangle that they could, because here's like the mosaic of the actual data set. So they were like, OK, we just need a rectangle for the press release, so we're just going to crop everything else out. But we went to look at this galaxy because we were really interested in that AGN feedback process. So here's an optical plus radio plus X-ray image of what's going on in this system. So optical is like the galaxy looking part, but then the radio X-ray is this feedback. The AGN is running into that host material, very similar to what we saw earlier with the splashing out with the aerial on the rocks. You can see the bottom side is splashing out to the left, and the upper side is splashing out to the right. And so we were trying to understand, we knew what was happening in the optical and in the radio and the X-ray, and we wanted to understand what was going on in the infrared. So we looked at the press release. The press release is so beautiful. They spent lots of time. This is what the data actually kind of looks like. It's not as beautiful, but it's very important. And so this is the first of 2 images. This one is just showing us tracers of star formation. And we're seeing that a lot of the star formation is going on in the dust lanes of this system. But we're seeing then where the contour is here. This is actually tracing that radio X-ray feedback process. And we can see that most of the star formation is not aligned with where that radio structure was. So they're probably not related. We looked at some different colors, though. And so these are tracers of shocks. This is like an iron line and a hydrogen line. And the only way you get this kind of emission is when you have some train on its path and it runs into something and it imparts a lot of energy. We say this is like a mechanical feedback process. And so we can see that it kind of forms, the hydrogen gas kind of forms this S shape that follows what the radio structure is doing. And so this is kind of a lower velocity collision. And then at several distinct points where the radio and X-ray are brightest, we're seeing faster collisions happening. And so what this is telling us is that there's some sort of feedback process that's going on, and it's relating the radio and X-ray that we see in other wave bands to these shock processes, these mechanical feedback processes processes that are going on. So we're going to zoom in then to this particular section, which I thought was kind of neat. It doesn't look very cool in the optical. This is a Hubble image in the optical. But if we look at the shock signatures, we can see that all of this looks like stars, but it's actually just like micro little explosions that are kind of going on here, like little supernovas that are all happening along the edge of this gas lane from the winds that the AGN has blown out and is now running into that dense medium. So here's like one line, here's a different line, it's actually a little bit stronger. And we know that these aren't stars because we have the images where the stars are, and we looked at where the explosions are happening and where the stars are, and they are not in the same place. So these are little dense shocks that are kind of going on, these little collisions that are happening all along the face of this dust lane. And so even though this is a really beautiful James Webb image, it's far away, so things aren't very sharp. So what I'm imagining is happening then is that here's the Helix Nebula. There's a star that's exploding in the center, and it's having a same mechanical feedback process along all of the material surrounding it. So we can see it kind of looks like an eyeball, but it's pushing away all of the material, and it's leaving these dense tendrils or columns of gas that are going on. And so we can zoom in. This is going to be a James Webb image then, where we can see all of these little rivulets of denser material, right? So you can imagine that this was once maybe like a slab of gas, but some of those portions of that gas are more dense than others. And so when you have this snowplow, this explosion front from that star pass through it, it's going to sweep away all of the low density material, and it's going to leave all of the denser material behind. And that's what's giving us these columns that are going on here. So this is kind of the same process that I'm imagining is happening with the AGN that we're looking at. But it's cool to have a more in-depth version about what's going on. So we talked about galaxies, we talked about black holes, we talked about active galaxy nuclei, and so a lot of them we're still trying to figure out, but with James Webb we're continuing to get more and more information about that, and we'll report back again next time and let you know what we've learned. But thank you very much. I'll take all of your questions. You, sir.
What's the closest galaxy with a black hole that's moving toward us?
That's Andromeda. So Andromeda is a galaxy that's very near us. It's faint, so we can't see it with our eyes, but you could look at it with a telescope and see that it's like 3 times the size of the moon in the night sky. It's really large. It is our neighbor galaxy. It has a supermassive black hole in the center, and it's coming toward us. And so in a couple billion years, we're going to have a really cool hangout sesh with a neighboring galaxy. But that's a long time from now.
So I have a question. When the collision was...
That's why you raised your hand.
Oh, of course. When the collision between Andromeda and Milky Way happens, how will the black holes interact with one another?
That's a great question, because so if you think about the center of the galaxy, and there's a supermassive black hole in the center, we don't know why that's there, first of all. But if you took out that black hole, the galaxy would still be orbiting along because of all of the mass in that galaxy in the first place. So for those two to interact, they would really have to be like seeing each other on the dance floor and being like, yeah, we're gonna like do this. Otherwise they might just pass by each other with the full mass of each other galaxy. And you can look up like galaxy mergers from Hubble, and you'll see these magnificent splashes, the antennae galaxies and stuff. So there's not a really good chance that they're going to hang out. However, if they do, they're gonna probably merge and create a really cool binary AGN, binary black hole system, and eventually merge and create a big gravitational wave experience. But I'm not too much more familiar on it than that. Hand back there, and then you.
The bubbles from our black hole.
The bubbles in our galaxy, the Fermi bubbles.
Yeah. Which masses of those bubbles?
Those are really tenuous, so there's not a lot of material there. And we think a lot of that radiation is filling up that cavity. And so we're seeing a lot of gas, like really tenuous gas that's emitting in like X-rays and stuff like that. But it's running into material surrounding it that we think is having an impact. But those bubbles themselves are relatively low density compared to the Milky Way itself.
I was off topic or not, but can you explain what a white hole is?
Nope. What's a white hole? I don't know. So I think this is nothing that we've ever seen before. I would guess that it is the opposite of a black hole, and it is producing a bunch of energy. I'm going off script. I would say maybe a white hole is what is the Big Bang, and it injected a bunch of energy into our universe, potentially. But that's just me shooting from the hip. I have no idea.
So with the black hole and the accretion disk, those jets that form, do those have a specific name? Maybe I missed it.
The jets? No.
Jets, yeah.
Oh yeah. So we try to come up with the anatomy of like what a black hole, an active galactic nucleus is, and so we do see these magnificent like jets that are. Let's say a galaxy is like 1,000 units wide. These jets can be 1,000 units. They can be huge. And so every cartoon of an active galactic nucleus that we draw now, we put that jet in there. And so they don't necessarily have to be in there, but we do think that sometimes the magnetic field can really wind stuff up and just whip it out to go out like 1,000 units. And so that travels along these jets, these radio plasma jets that we see.
Okay, thank you.
You, hat, yep.
Do you think perhaps the galaxies formed around supermassive black holes? The galaxies created the supermassive black holes?
That's what we're trying to figure out. So we don't know how they got there and which was first chicken or the egg in this situation, right? So we're finding out, what are we finding out? We're trying to understand these things that Webb has been detecting recently called little red dots. We don't know what they are, but one plausible idea is that they're supermassive black holes without much of a galaxy around them. So that would say that the precursor is a supermassive black hole, and then the galaxy forms around it. But like I said earlier, you could take the supermassive black hole out of our galaxy, and the galaxy would still keep trucking. Like, it wouldn't know that it was gone. So maybe it's an effect of everything that kind of gets down into the center. I'm picturing in my head right now when you have one of those little water funnels that maybe is going down into the drain, and you see like things are spinning around, and they always like start spinning around really fast when they get down to the drain. So maybe material in our galaxy can kind of do that too, and that coalesces into a black hole that just continues to grow and grow and grow and grow. But I don't know. But that's what we're trying to figure out as part of our research that we're doing.
I see your hand. Yep. I've always had a problem conceptualizing the singularity as an infinitesimally small thing. Me too. To me, it seems like you can't destroy matter. There's got to be something there, even if it's the size of a baseball.
Totally. So when I say like I'm an AGN astronomer, I really care about like how it messes up the host galaxy that it lives in. And so I don't have the physics chops to be like, oh, well, it's actually what's going on is this. So I too I have a hard time like, is it really, there has to be some surface that everything becomes an infinitesimally thin onion shell around or something like that. So I hear you, but I don't have a better explanation than.
Does anyone have any idea how to estimate something like that?
Probably. George can get that guy in next time. So yellow shirt, I see you with the hand. Yep. Is it yellow Pokemon? Yep.
So is it possible for a redshift to go off the optical spectrum?
Yeah, totally. So let me go. I'll make a slide. I have slides. Yeah, so that's one reason that James Webb is so cool, is because it helps us see things that we wouldn't see otherwise. So like here's what we do with Hubble is we understand, oh, we can see this galaxy with Hubble and we understand it, great. But when it goes to a higher redshift, if it's further away, all of a sudden the photons that it's emitting, we can't see them anymore. So Hubble no longer does the job for what we want it to do. The photons aren't in the optical anymore. They're in the infrared. So that's one of the reasons that James Webb is so cool, is because it is sensitive to the infrared photons. So now we can learn about those galaxies that are further away that we couldn't see before as well. And now we can start comparing them to the galaxies that are nearby. Are they different? Are they the same? We don't know. We're trying to figure it out, because do things change over time? We're trying to learn that. But yeah, so to answer your question, yes, things can redshift out of the optical into another waveband. You.
Can you roughly describe like the velocities and properties of some of the very large stars that are very close to the black hole in orbit? Are there...
Probably. So no. All right. I can't give you a number. But there's a really cool video. So there was a Nobel Prize that was assigned to an astronomer named Andrea Ghez. And so one of the reasons that she got it is because she had confirmed evidence that we have a black hole at the center of our galaxy, because she led a team that tracked the movement of stars around the center of our galaxy. And the only reason that a star that they saw travel the full loop, and the only reason it could go that fast around one part of it, is that there had to be something stupid dense and stupid small right there to make that star go that fast. Whatever that fast is, I don't know what that is necessarily. But you could go look up like stars traveling around our black hole, and you could learn about how fast they could travel and not get split apart. Right? You.
So as I understand it, accretion-based cause X-ray variability and relativistic jets. So would you detect AGNs by searching for variability?
So the question was, can we find AGN by looking at X-ray variability? Right? Okay. So totally. One of the ways that we find AGN, period, is by looking for X-rays. The only way that we can see a lot of X-rays coming from a galaxy, typically, that's far away, is because there's an AGN in the center. So just finding the X-rays is good enough. But then if we're trying to understand like the processes that are going on in that black hole, like how fast it's eating things, we can look at how that X-ray flickers over time to understand like, oh, there's a bunch more material that just fell in right there. And then how does that change with other wavebands that we're looking at to see, oh, this is happening right in the middle because it's X-rays, and then, oh, the optical gets brighter later. So maybe something happens a little bit further away.
How many black holes have been discovered?
6, 7 million, I don't know. So the understanding is, I mean, when we looked at that picture from the Hubble Deep Field, right? Those are all galaxies inside that picture. And from our best knowledge, like every single galaxy, not every single, sorry, most galaxies have a supermassive black hole at the center of them. So this is just like one tiny picture that we took, and it's not representative of the entire sky, but you could imagine these are everywhere. So yes, each one of these has a supermassive black hole. Each one of these also has billions of stars. Each one of those stars probably has at least a planet or two. So it's crazy to think about how much is out there that we're still trying to count.
But the first black hole was discovered not too long ago.
So discovered is, I don't know how to say we discovered that. I mean, so we observed a black hole, but we were pretty sure that, I mean, from our work with AGN, we're like, man, whatever is really bright in this galaxy is also really bright in that galaxy. And we're also pretty sure that we're pretty sure, again, that there are black holes at the center of every one of these galaxies. So if we're seeing like this effect of of gravity to form what a black hole is at the center, and then we're seeing them go off with all of these X-ray sources that I was talking about earlier, then we were like, man, a lot of these things probably have that really bright thing in the center. And so we're pretty sure, again, that most of them, any scientist worth their salt is never going to tell you 100% of anything that's ever true. So we're pretty sure, though, that most of them have supermassive black holes in them.
Let's maybe take one more question, and then you can come and talk to the speaker. One more. Yep.
Okay, so when a black hole moves a photon's direction, does that photon accelerate, and does that mean that a black hole might cause
Oh man, so this is a physics 102 thing, in the sense that it's not accelerating in this, oh man, no, that's a good question, because like, guys, speed and velocity are two different things, right? So it has a velocity, but it's changing direction, so it's accelerating in that direction, but I think the speed of the photon is still constant. So yes, the velocity is changing, but it's not, it's just accelerating in a different direction, but it's still traveling that same speed. Are there other physics people in here that can confirm that I said the right thing?
Anyway, on that thought, let's thank our speakers.
Okay. I have these pictures, I have these stickers. Please take them with you. I don't want to take them home.